Huh?
That's pretty good.
It's time to go.
Oh, you're doing
That was good. That was good.
Gosh. All right.
There's the 10 people.
Here's Pluto. All right. Any questions from homework stuff? I had several good ones during office hours. I don't know if anybody else came with any questions from all of the work you're definitely doing.
88.
88 from 5.4. 5.4 you said?
5.5.
5.5. Oh, all right. This is a neat one. All right. Well, you know, they're all neat. 8. No, I lost somebody. Shoot, man! I thought I had one more. So this says if f is continuous and the integral from 0 to 9 of the function is 4, so we know this is true. Fine, we're trying to figure out what this integral would be. Right? Let's see, go ahead. Yeah. Now, they put this as number 88. You look at it, it looks really freaky. This is easy as shit. The car's like, thanks, man. But I just want you to realize they put it at the end of the section, all this kind of stuff. They kind of hyped it up to be this crazy hard thing. Is there an inside function in this one?
Yeah.
Yeah.
That's
Right? So if you let, and that's all I'm going to say. I mean, now you're going to do use substitution. Now listen, real quick. Let me ask you. If this is true, what about this? What would that be? If this is true, what's that?
4.
It's 4. Right? You guys understand? Give a shit what variable, whatever variable I use, the area, because the function doesn't change. Did I change the function? No. So whatever that is along the w-axis, it's going to be the same area because it's the same shape. Yes? So what if there was a u in there? What would this be? What would that be? Okay, that's all I'm going to say. That's too much. I said too much. Okay. Some of you guys are like, you didn't say anything. Anything else? So there's certain problems I've assigned in the homework to push the concept a little bit to show you. Like that one we talked about a few times, the one with the 3 different shapes, and you have to see if they're the same area. And that's just trying to get at the idea that U sub really does smoosh the shape. It reorganizes the area of God, just like we did with the circle and the triangles, and we opened it up, we smushed it and made it right. It's the same idea, right? Okay. So integrals mean a few different things, but fundamentally they mean area. So everything we kind of do with an integral can be thought of in terms of shit happening to an area. Maybe. Okay, all right. Anything else from homework? Anybody got into chapter 6? Or anybody else got into chapter 6 yet? I know. Okay, so I want to start off with something I haven't worked with too much with you guys, but I just want to show you the usefulness of this. Let's say I've got this going on. So I've got that function there, right? And I want to know this area. There's 2 ways I can do it. Now, how is that different from the areas we have normally looked at? Normally, when I give you a function, I ask you to find the area where?
In terms of x, or like along the x-axis.
Yeah, in terms of the x-axis, right? So I would normally ask you to find this area, the area under the function, yes? If you did find that area, if you did find this area, and what would this area's, how would I find that area? In there, how would I find that? You can do it.
Just integrate
Integral from,
0 to 4.
no, I like what you're doing, hold on to what you're saying. We don't have shit right now. If I had shit, I could do what you're saying we're going to. So hold on to it. But just to find this area, wouldn't I do 0 to 4, right? Keep going.
2/3.
Oh, you're trying to think ahead. No, don't think ahead, just what we're going there.
Oh, yeah,
Don't do
root
anything
x,
yet.
root x.
Yeah, root x, so let me put next one out. All right, let me stop for a minute. All of you have to understand what I just did, no problem, that's easy as shit. If I said, here's square root of x, find the area, that's, you're like, oh, that's easy. That's where you must be right now. It's not a u sub, it's not the weird, it's just a straight integral, find the area. I know we eventually want this, but right now I'm just saying, if I wanted this area, that's what I would do. Right? Go ahead and do it, real quick. Do that. Yes. Are you done?
No, that's good.
So what is the antiderivative of x to the 1/2? So then I have to do 2/3 times 4 to the 3/2. And when I put a 0 in, I'm gonna get 0. Now here, watch this, everybody. 3/2 power means what root? Second root, right? What's the square root of 4? Cubed. 8 times 2. All right, so get your calculators and put them away. Shit, right? One reason why I try to get you guys to do more things by hand is to keep things alive, like what the shit does a 3/2 power mean? The less you do it, the less you're gonna remember it. So you just throw shit in the calculator and you get 5.3333. Doesn't mean anything to you, it's just a number. All right, so that again, what does that represent? Yeah, that represents this area in here. Now, come in with what you're saying. Now that I know this, how could I figure out this area?
Solve for y and.
No. I like what you're saying, but no. We're gonna do that next. I know this area is 16/3, and I wanna know this area. Isn't that just,
Take the area of the whole thing.
yeah, what's the area of the rectangle? 8. So then what's the area of this sliver, this piece?
8 minus 16 over 3.
8 minus 16/3. And 8 minus 16/3 is 1 whole 8 minus, let me see if I can get you good. Ah, screw it. I'm not going to do it some weird way. What do you get? 8 minus 16/3? 8 thirds. Now, that wasn't too bad by itself, right? And of course, the function is really nice, all this kind of stuff, right? But there's a more direct way to do this area, right? In fact, if you look at it this way, isn't it the area between the function and the axis? Doesn't that directly match up? Would I have to do extra shit to get the area then? No. Why did I have to do extra shit to get this area when I looked at it from the x direction? Because it's not between that axis and the function. I really want you guys to get that. What does an integral directly mean? The area between that axis and the function. That's what it really tells you. I had extra work because the area doesn't like hug the axis. It's the other side. Okay. If I look at it, everybody actually physically do this. If I turn my head, then it does become a normal area. It does hug the axis. Yes? You guys understand what I mean by hug the axis? Doesn't this area hug all? What does the axis hug? So if I change everything in terms of y, if you solve this for x, what do you get?
Y squared.
Y squared, right? X is y squared. So now I can integrate dy. Instead, what is y doing across this region? What is y doing?
From 0 to 2.
0 to 2. Yes. And what do I put inside? Y squared. What is the integral of y squared?
1/3.
Yeah, 1/3 y cubed. What's 2 cubed?
8.
8. So 8/3 minus 0, 8/3. All right, which one took less time? So in some situations, I could do it either way. Just one of the ways is quicker. In some situations, only one way is doable. We saw one like that when I tried to have a natural log of x. Remember that? What's the integral of natural log of x? We can't do it yet. We don't know what that is. But if I flip it, if I solve for the other variable, that's e to the y. And that integral is easy as shit. Maybe? All right. Okay. Anyway, so I really want you to understand a couple things. Why would I want to go change my variable from dx to dy? Why would I ever want to do that? Well, one thing is sometimes it's a lot easier, or even more importantly, it's possible that, right? The function I'm given might be impossible to do. Even after you take Calc 2, there's functions you can't do, integrals of in Calc 2. Even after you take every calculus on the face of the earth, there are integrals you can't do by hand. And that's why you have a class called numerical methods. Anyway, enough of that shit. Okay. So that's a little kind of aside, but we're starting to get into a region where it can be either dy or dx, and I want you to start to understand why I want to do one or the other. Okay. So last time we got into this disk method. And I think what I want to do, let's do this. Okay. I'm going to give you this, and what I want you to do is to sort of ignore the colorful, shiny side, all right, just for right now. We're going to do the back boring side. Okay. All right. Any- Go ahead. All right, so what I'm going to do, the back looks pretty sparse, yes? But I'll tell you in a minute what the hell it's supposed to mean. I really should have done this first, Jeff. Hold on. Do it with you, yeah, maybe. It's always exciting when I, yeah, whatever. No, clear. I'm gonna use a pen, I might as well go all in. Alright. what in the world is happening back here? Well, there's something neat that we're going to talk about. So teardrop. Let's see. So if you ever wondered what the equation of a teardrop was, it's right there, and you didn't see it. Okay, so that first problem gives us what I call walls. Man, what happened to these rows? So this describes a region that we are going to rotate around the x-axis. So obviously the very first most important step is to give yourself a decent sketch of the region. You never have to draw 3D. I've said that before, and I will continue to say it. Right? So what's kind of most important? How do I want to draw the entire parabola? No, because it tells me I'm going up to x equals 2. What does y equals 0 mean? Ooh, look at that.
The x-axis.
Yeah, y equals 0 is the x-axis. I love it. So x equals 2 is here. Let's kind of, should I? No, it doesn't matter. So here's 2. That's amazing. So that's going to be one wall. And then I have a parabola. I should say first quadrant, but I mean, there should be enough. Y equals x squared, 0, 0, 1, 1, 2, 4. All right, so I can graph x squared easy enough. So here's one wall is the parabola, one wall is x equals 2, and the other wall is the x-axis. So a lot of the problems in this section will basically give you your region defined like this. So those are 3 walls. So what region do those 3 walls enclose? Well, that region. That freaky triangle somebody sat on, right? Okay. I'm pretty sure we basically did this problem the other day, but let's see. So I'm going to rotate it around the x-axis. And when I draw my region, I might as well give myself a reminder, a visual reminder of what I'm rotating around. Okay. So here's why you don't have to graph 3D. If I have a 3D shape, like let's say I have a sphere, the radius, does it go across the entire shape? The radius. Does it go across the entire shape? The radius. Where does it start? Center, right? So isn't that sort of like half of it? So I really want you guys to understand, if I did rotate this, like that point right there, if I rotated it, what would the radius be? It would just be right there, wouldn't it? So I don't need to rotate it. I don't need to actually do it myself. I know it's going to be rotated, but can't I identify all the radii from this? Now, why is the radius, like, pick an arbitrary x, let's all do this one. So you can pick any position you want, but I'm going to pick this one, and that's x. What would the radius look like? It would look like a line, Jeff. No, but I mean, where would it be? Where would it start?
Start at 0.
Why? What did we say earlier? Sphere, the radius starts at the center. If I take a region and I rotate it around an axis, isn't that axis effectively the center? I really want this to make sense. So right there, again, I'm not going to draw any 3D on this, but if I did rotate this, wouldn't it be a sphere? Wouldn't it be a disc? Right there, wouldn't it be a disc? If I rotated this, so if I rotated this dot, it would make this disc, right? And the radius would be from the axis to there. Maybe? Are you guys all right? So again, you don't have to do this, but I'll go ahead and do this. So here's the point right there, right? If I rotate it, it's going to go there. If that helps at all. So it's going to make that circle, right? And any x value I choose from 0 to 2 is going to make its own circle. What's going to be true about that circle? What's going to be different about the circle for the next here? It's going to be smaller, of course, right? And what's going to be true about it here? Freaking big, right? So let me do it at the extreme. Jeff and a half. Okay, there. So if I did it here, it would go one. Big ass circle. And if I did it down here, it'd be. Okay. So really, I need you to understand. Thinking ahead, what would the integral for this go from to? 0 to 2. And what I'm doing is, what does an integral mean? It means I start at 0, and then I do a little width, and then I do a little width, and every time I do that, I'm going to have a disk, and I'm going to take its area, I'm going to add it to the next area, I'm going to add it to the next area. Right? That's what integrals do, is it's infinite sums. So I'm going to take that disk area, plus the next disk area, plus the next disk area, right? So I'm scanning along this axis, and as I move along the axis, I hit the next disk. And I move along the axis, I hit the next disk. I move around it. So that's what I mean when I say scanning along the x-axis. Because as I move, I pick up another disk. As I move, I pick up another disk. Right? And they keep getting bigger as they go up, in this case.
So is the disk at 0, like if you took the radius at 0, 0, and then
There would be a disk of radius 0, which is a way of saying the biggest fish I caught was 0 inches long, which means I didn't catch any fish, right? So at 0, 0, there is no disk. There is no disk. Yeah, okay. That's what the matrix one. So, I have just said a lot of shit that you don't have to have in mind when you do these problems. I'm talking extra stuff. I didn't have to draw that disk. I didn't. In fact, let's start over. Region. I pick an arbitrary position, and I pick another one to figure out my radius. Where did I start my little, well that doesn't, well, I really hope you guys can see. This is just the tick mark, and there's my arrow. Where did I start my arrow? At the axis of rotation, right? And then I drew until I hit the wall. Let me put this back in. So what is that radius? How long is that radius? Yeah, the top wall, this is x squared, and the bottom is 0, right? So it goes from y equals 0 to y equals x squared. So of course it's x squared long, right? Why does that make sense? Because as I move up, isn't that radius getting longer? Yeah, it's getting the square of the number I'm at now. So I've got everything I need to set this up. What's the area of each disk? What's the area of each disk is what shape? Circle. So what's the area of a circle? Pi r squared. Don't we know what r is? All right. So what do I want to do? I want to take every disk and I want to add them up. Right? And this is a function of x. And I'm going from 0 to 2. So all that says is let x go from 0 to 2, and as I step, I get a disk, add its area to the next disk, add its area to the next. That's all that says. So what is r again? R is x squared. I got to square it, right? All right, do that real quick. 32/5 pi. Is that cool? Inside you get x to the 4th. Its integral is 1/5 x to the 5th. Okay.
This is a dumb question. Can you do how you did the integral?
Well, what's x squared squared? And what's the integral of that?
Oh, got it.
Yeah,
okay.
yeah. So I mean,
simplified.
simplify the inside before you do anything. I don't have an integral rule for a function squared. I don't. I do have an integral rule for x to a number. Yeah. So what is different? What is different? Let's see. Let's go here. What's different here? That looks like the same. It's got the same walls, don't it? It's got the same walls. But what's different? Oh shit! I can rotate. I can rotate. I can have a region, and I can rotate it around any axis I want to. And to be really honest, you could rotate it around a diagonal axis, but we're not going to do that in Calc 1. I really want this to make sense. The first one we did, we just chose the x-axis, we rotated it, right? We got like this funky cone-shaped deal, yes? When we rotate it, we get a cone-shaped kind of deal. Okay. Here, let's see. All right, so let's graph our region again. It's the same region, yes? It's all the same walls. So it's the exact same region. But where's my axis of revolution, my axis of rotation? Let's put that in here. It's going to be at y equal -2. Where's that? What kind of line is that? Yes, good. Flat line at -2. Bam, bam, bam. Bam, 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 bam. Bam, 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 bam. Bam, bam, bam. Yeah, bam. So I really want you guys, in fact, for a minute, let me just do this. Pi. So if I took that and I rotated it around, so here I am, I'm the axis. I'm holding the shape. Are you with me? Here's the shape, right? I'm the axis, and I turn. Right? Do I have space here to be in? Am I like encapsulated in this thing? If I rotate that, what's going to happen in the middle?
The space.
It's going to be empty space in the middle. It's going to be kind of like a bundt cake pan. Have you guys ever seen that? You guys know what I mean by a bundt cake pan? They're neat. It's a bowl, but there's a thing coming up in the middle that opens out of the bottom. It's like a hollow thing in the middle. I don't know, so let's look it up. Okay, I really want this to make sense. I'm gonna have an empty space in the middle, right? In fact, again, you don't have to do what I'm about to do, but I'm gonna try to do it. If I did rotate this around, Jeff, you're a little bit off, that's okay. If I did rotate this around, it would do this kind of thing. Can I make this work? Yes, I can. No, I can't. What's wrong with me? Oh, I see what I'm doing. Oh, God. Let's try this again. I'm so happy I got so many copies of this. Okay. Okay, back up. I didn't really give myself enough room to do this correctly. So this would go, I really want, this is going to be interesting. This is going to go, so it's going to go way the shit over here. This is going to go over here. Do you see how I'm going to have this empty spot in the middle? If I rotate that around, I'm going to have an empty spot in the middle. All right, I'm using so many pieces of paper. Okay. Let me redo this.
How many trees have you got for this?
The right amount. All right. Okay. So here's the trick. What did I say earlier about the radius? When you draw the radius in, it has to start where? the center, at the axis of rotation, yes? And then you start from the axis and you go until you hit a wall. If I start at the axis, what's the first wall that I hit?
Or
Y equals
zero.
0.
Yeah, so I start here and go there. And that's going to define the empty chunk. So listen, let's see. Maybe I should have done this first. It's all right. It'll be all right, Jeff. If I rotated this square, you got this square, if I rotated it around and did all the stuff we did there, I would find the volume that the square makes when I rotate it around, right? Am I not going to subtract that from rotating this whole thing around? I'm going to subtract it out. It's what I call a cookie cutter problem. I'm going to cut the middle out. The book calls it the washer method. What does a washer look like? And it's got a little circle in the middle, right? So it's got this thing, it's got a hole in the middle. Isn't that basically what we just said that's going to happen? I personally don't think we should call it the washer method because it makes it seem like everything's different. It's a whole new method. No, it's two freaking discs. There's a disc on the outside and there's a disc on the inside. I just have to subtract the one on the inside and one on the outside. So there's an inner radius, right? So a washer looks like this. Isn't there an inner radius and an outer radius for a washer? So this is the inner radius. And somebody tell me, no matter what I picked from 0 to 2, does the inner radius change at all as I move? What is the inner radius always? 2! How do you know it was 2?
Y equals 4.
Because that's 2 away, isn't it? What is this? Isn't this y equals 0? Yes? This here? It isn't this y equals -2? Yes? Right? Now listen, there's a reason I'm doing this. How do I always find the length of something I've drawn on a graph? Big minus small. In this case, 0 minus -2, which is 2. Did I really need all that shit for this? No, I can see it's freaking 2 away. But you know, later it's going to get a little more interesting. Okay. What's the outer? Now, start at the axis again and go past the first wall because we got him covered. What's the next wall I hit? So let's try this. This is y equals what?
X squared.
X squared. And this is y equals -2. Yes? So what is the outer radius? I mean, I really desperately want you to understand this. Inner radius on this one is pretty easy, but still it's big minus small. Right? Start from the axis and go out. How far is this from this? Well, it's that minus this, yes? So it's x squared minus -2. So it's x squared plus 2. Now in this example, do you really need to think about like that? No, I didn't. Because isn't this freaking x squared? So anywhere along here, it's going to be x squared plus the extra 2. So of course it's x squared plus 2. But again, later it's going to get a little harder to kind of tell. And what do you always do? Draw the thing in, take the bigger one minus the smaller one. There's your radius. Okay. So, since I'm using discs and my axis is parallel to the x-axis, this is going to be integral d what? The beautiful thing about the disc method is whatever axis you're rotating around, in this case it's basically like an x-axis, right? It's integral d that. So this is going to be integral dx. Okay. From what to what? So now that you've identified its dx, you know to look at the x-axis for from what to what. So the region goes from, I really, see all this extra shit I have here? You're like, yeah, I do. Well, what's the region go from to? 0 to 2. Now here's the trick. Oops. What I need to do is I need to take the area of the whole thing minus the area of the inside. Sort of like we just did a minute ago. I can't remember what we were doing. Does that make sense? Like I have, how many guys, anybody ever baked before? Or have you ever watched somebody bake something? And they roll out dough. Let's say they roll it out, it happens to be a circle. And I'm gonna cut the middle out. That's basically what we're doing. So I take the area of the whole dough minus the area of what I took out will be the area of what's left. Ooh, that's amazing, right? So this isn't different from discs. This is just two discs, an outer one and an inner one, and I'm subtracting them because I'm taking one out. So basically that's what I put in here. So I can take my pi out, and I want the r outer squared minus the r inner squared. What did we say that r outer was? X squared plus 2, right? And what did we say that r inner was? 2.
So can we just write 4 instead of 2 squares?
Of course you can, of course you can. But I just want to show you things, how it's getting put in there. Now, take a minute and do that integral. This should be the easy step. Okay, let's start doing history. Right, is that cool? The 4's cancel. And then that's an easy integral to do. Okay. When you plug all that stuff in, 0 is going to be 0, so I just worry about 2. I get 32 fifths pi, which looks familiar. And then 2 cubed is 8 times 4 is 32, so bless you. Plus 32 thirds pi. And then you can put those together out here. 15, 38, 15, so 8. 256 thirds pi, maybe? I don't know. All right. So real quick, what was the volume of the first one we did? What was the volume of the first one we did?
32 pi over 5.
Isn't that this? Right? All right, that's just, okay. So isn't the volume of this one more? Is anyone concerned because we did take a chunk out of the middle? But isn't this one, I really want this to make sense, doesn't this one make much larger circles? Because the axis of rotation is further away. So it's like if this is the axis and I go, whee, I make a circle like that, right? Or if the axis is way over there, whee, I'm gonna make a big ass circle around this thing, right? So it's like, this has a certain area. Ooh. If I start with a big ass circle and I subtract that out, isn't this area bigger than that area? Okay. So yeah, if I take my axis and I move it further away from my region, it's going to rotate further out. I'm going to get more shit to include in my volume. So it makes sense this one's still bigger. Maybe? Okay. So there's two levels to these problems. One is just the physical, what the shit's going on physically, and the other one is computational stuff. Okay. What about, so here, let's see if you guys remember. I give you two walls. Who remembers what we need to figure out first before I graph anything? I want the region is defined by those walls, so I have to know where those walls do what with each other. Where they. So if one wall is this, and the other wall is this, what's the most important points?
Oh, intersection.
Okay, good. Right? Because I give you two walls. I want to know the region that's bounded by it. I'm going to rotate around the y-axis. Ooh. So what do I have to do? I have to do what first? I have to set them equal to each other. I got to know where the hell they meet. So this is 6-1. One of the big things in 6-1 is where the shit do these things meet, and that helps me figure out what interval I'm going across. Okay. So the first thing I got to do here is some algebra. Is that cool? Right? X squared equals 2x, x squared minus 2x equals 0, factor it, 0 and 2. So the points are 0, 0. Right? Plug the 0 in, get 0. And the other point is 2 for x, and when I plug a 2 into either one, I get 4. Yes? All right, so I can plot. So what's beautiful is I can just plot 0, 0 and 2, 4, and then I connect them. Now this one, parabolic, yes. So it's going to go like this. This one, linear. So it's going to go like this. And one little thing I want you to realize, something that I should have changed up here. When you do these problems and you're drawing a rough sketch, did I really need this, and this? Don't I know that before I started to graph anything? I knew it from right there. So when you do your homework, you could just do y-axis, x-axis, focus on there so you can zoom in, yes? Isn't this a little bit skinny of an area to try to work in? So you can be nice to yourself, and you can zoom in. You don't have to have this whole thing. And then here's the region I'm working with. Let me draw. Holy shit! Zoom into that thing so they can draw shit in there. Okay, maybe. So I was a little evil to myself on this, but not terribly evil. All right, what am I rotating it around? Y-axis. So what's kind of sucky about that? My integral's going to have to be what? Integral d what?
dy.
Oh shit. Why am I concerned? Why does that make me go, oh shit?
Because
A little bit.
Everything's
Everything's
in
in terms of x right now. All right, so it's not really that big of a deal. But do you guys understand how important that step right there? Integral d what? You should not do, you graph the thing first, but you shouldn't do any freaking calculus work until you're certain you have the d what correct. So if I want to use discs, it's got to be dy because I'm going around the y-axis. The minute I put that down, I know my functions have to be functions of y. It's the only way the integral is going to work. So in this case, it's not that bad. Are you guys agree with me? What if I solve this for x, what do I get? Yeah, why is it not plus or minus square root of y? I'm on the positive side, right? That's beautiful. And of course, this becomes
Y over halves.
y over half is an interesting way to say it, but I'll take it. All right. Gotcha. Let me stop for a minute. What's most important when we're doing a problem like this together is, why did I do what I did? I let the problem tell me. About the y-axis, I want to use discs right now because it's the only damn thing I know, so it's got to be integral dy. Just a little preview. What if instead of y equals x squared, what if it was y equal, what do you got, Jeff? X squared plus 3x minus e to the x. If you are able to solve that for x, teach me. Now, as I say that, there's kind of a rough way to school, but I mean exactly give me this. Give me x equals a function of y. Can you see how that's basically impossible? Because how would you free that x up? Wouldn't you have to take a natural log? But then aren't these stuck in a natural log? Do you see, you can't, it's like whack-a-mole. Yes? So you can't solve this for x. So if this was, if instead of y equals x squared, if the other wall was this, could I use discs? Could I? Again, if instead of x squared, it was that shit. And I know that discs requires this, doesn't it? Why does discs require this for this problem?
It's about the y-axis.
Because I'm going around the y-axis. So this has to be here for discs. But if it was that, can I solve for x? Which is what I need to do, right? I can't. So I would need some other method, maybe the method we're going to learn in section 6.3, that would actually require this to be a dx. So right now we're learning discs, and anything that discs can't handle, shells can. They kind of complement each other. If discs have to be dy, shells have to be dx for that problem. Okay. Just to kind of look ahead. All right. So what do I need in here? I need to figure out my R outer and my R inner, correct? And by the way, on the other side you can see here. This is the washer's method. So you've got to reference this. Okay. So can you guys, and we're going around the y-axis, right? So there's my little y-axis thing. Can you try to draw in? And can somebody right now tell me, what am I going from to for this? Integral dy, so what's it going from to? 0 to 4. So can you pick an arbitrary place in there and draw in the inner radius? And one other thing. Okay. So if you're sitting there, are you asking yourself, all right, that first problem, did we need an inner and an outer radius on the very first problem? Very first problem, did I need an inner and an outer radius? Why, yes, I didn't, right? But on the second problem, we did. So you could be sitting there saying to yourself, how the shit do I know, right? This is basically all mathematics. How do I know when to do this thing? So let me ask you this. On that first problem, was the region hugging, this came up earlier, is the region hugging the axis of rotation? Yes. So will there be a hollow middle? No. So, for example, if I have, let's see if this will work. If I have this and I'm the axis of rotation, if I rotate, isn't it not, there's not going to be a hollow middle, is there? But if I go like this, if my axis is away from that region, I'm not hugging the region. If I rotate, there's going to be a hollow middle. So I'm desperately trying to show you visually, how can I tell when I need to do the R outer, R inner? Is my region hugging the axis of rotation? No! So I'm going to need R inner, R outer, right? Yes?
So for it to be hugging, it kind of has to be like adjacent along all.
The whole way through, it's got to be adjacent. The minute it kind of leaves it, I'm going to have an inner radius there. So that very first problem, throughout the whole interval, it was right next to it. It started at that wall, right? But here, y-axis, it's not starting at the y-axis, it's away from it. So if I drew in the inner radius, what's the first wall I hit? What do I hit first? So I'm going to start from the axis, and I'm going to draw out from the axis. And you can pick any point you want to. Yeah, the very first thing I hit is y/2. Is that cool? You guys see that? It's that simple. You always start your radius at the axis, and then you draw until you hit a wall. And you say, okay, what is that? Right? Well, it's y/2 because this is basically y = 0. Right? So what's our outer going to be?
Root y, or root x. Yeah.
Say again?
Root y.
Root y. Okay. So do you notice how important it is to draw a decent sketch of the region? And again, what was the purpose of pre-calculus? What was, like, if I had to sum it up in one word? Graphing. If I summed it up in 2 words, graphing hell, right? It puts you through it, yes? That's its job. So that when you get here, I'm not making you draw perfect shit. You just have to draw it well enough, and you've gone through the shit. You've gone through hell. And you're like, this guy just wants a sketch. Thank the gods. But the worse your sketch is, the worse your work's going to be, for damn sure. So now it just plugs it in, right? Pi 0 to 4. What's the R outer?
Root y.
And that kicks ass, right? Because I'm going to square it. That's beautiful.
That's just y.
Minus R inner?
Y.
It's just 0.
No, it isn't.
Oh,
R inner is y/2. Right. And now it's the easy step. Yeah, I'm a Jeff. Stay with me. Is that cool, by the way? Y squared over 4 integral is y cubed over 12, because you're going to put it over 3 down there too. Yeah, you just plug shit in. Right? Sorry. This is the less interesting part to me, because you just plug shit in. Who cares? So let's see, you get 16 over 2 is 8 minus 64 over 12 is 32 over 6 is 16 over 3. So you get 8 minus 16 thirds, which is 8 thirds. So you get 8 pi over 3. If I did all that right, who knows? Sure. Let me see. Let's do this right now, before I forget. What time is it? Okay, good. Let me set something up for you real quick as you guys ponder questions you might have. I'll get to this today. Go on. You. I don't want that one. Come on. This one. Yes, okay. Okay, so we got y equals squared. Okay, I'll show you this. Wait a minute, what happened? bit better. Let's see what you guys think. Just to give you another better visual. So I think you're gonna mix up. So doesn't that basically look like, right, the region we were working with? So now if I think I got this set up right. Let's find out. If I rotate it, I'm gonna end up with a little bowl. Isn't that kind of neat? A little bit. And look what else I can do. Look what I can do. All right. Are they gonna do the wrong thing for me? Probably. Oh, yeah, it's gonna do the wrong thing. You assholes. Yeah, this is more set up for, not for washers. This doesn't really work either. Rawr. It's alright, Joe. Anyway, so that's what it looks like truly when you rotate it. So what we're doing, we're not finding the volume of that's in here. You understand? I'm finding the volume that actually has stuff in it. Right? Because let me take it back. Let me do a cross section. There. Do you see this? And it kind of goes around, right? I'm looking for that volume. So if I was to construct a bowl, what volume of material would I need to construct the bowl? Does it make sense? Which is different from what's the volume of the bowl, yes? So what we just did is we found the volume of material I need to make this bowl, not how much shit the bowl can hold. How did I figure out how much shit the bowl can hold? We do sort of like we did that other problem. We figure out the volume of the whole, like put a top on, find the volume of the whole thing, and then subtract the volume we just found. That would be the volume. Okay. You guys semi with me? All right, I got about almost half of you are with me. Okay. And if somebody reminds me, I can send you the link to this website. What's really cool, let me kind of show you this. If you first go to this, oh, Jeff, that's really cool. You just go to this website. Oh, shit, half. Let me try this again. When you first go to this website, it looks like this. But if you go to examples, solids of revolution, you can pick any of these. And then you can go in and change the function, right? Now, I am not going to devote part of this class to learning all the ins and outs of this. So this, you can use it at your own leisure, right? But you can change the function, and then you can rotate it. And do you see axis of revolution, y equals 0, right? So let's change that to x equals 0. Yeah, that'll work. Whoa, dude! So it's the same region, and if I rotate it around the x-axis, that makes that, you can tell what it's going to be. If I rotate it around the y-axis, let me do this slowly, that's what it's going to look like, right? Whee!
I remember I used to do this with my 3D online design.
Yeah!
I just like made something, I rotated and see what it made.
It's a beautiful little flying saucer. Okay. There, I can let it just play. Just play. Now I feel like I'm a flying saucer salesman. This is our Model 7X. The improvements over this. All right. Jeff. I'm going to turn off the rotating flying saucer.
No, I think that's a very crucial part of the lesson.
Yeah, it was, and it was there, and we're done with it. Now it's rotating just for me. Stop. So let's look at this last problem. All right, so what's the first thing you should do here? Before you try to graph anything, what's the first thing we should do? Yes, I gotta know the points where they meet so I can see what region they enclose. Okay. Why didn't I have to do that on the first ones? Because I gave us so many walls, I just had to like draw the walls up golden. Here, got to figure out the points of intersection so I know where to start and stop. So I'd recommend you add y squared over. So you keep the y squared part positive. That makes factoring much easier. Oh, here it is. Yeah, this is good. Okay. Alright, so what do you guys get for the y values?
Negative 1 and 1.
We do what?
I was looking at the bottom.
2 and negative 1.
Alright, so here's where you gotta be careful. What are the actual points of intersection then? I would put a 2 in here and a negative 1 in the y positions. Because that's what I know y is at each point. So when I put a 2 into either one, what do I get for x? Negative 4. And when I put a negative 1 into either one, I get negative 1. Okay. Just to give myself some more room to play with them, I'm going to use one of my earlier debacles. I'm going to put that over here. So negative 4, 2. Negative 1, negative 1. So it's beautiful when you find the points of intersection. You plot those, and then you just gotta fill the shape in the middle. It's kind of awesome. And again, I just need a rough sketch, right? So let's see, negative 4, 2. And negative 1, negative 1. So again, if I was graphing this myself without somebody giving me the x, I would kind of zoom in on that part. Now, in between those, let's see if you guys can get this. All right, all right, how do I say this? X equals negative y minus 2. That is easy as shit. Because I have 2 points. And what kind of thing is x equals negative y minus 2? What kind of thing is it? Graphical element. A line. So I don't care what I just connected dots. Can't beat that. Right? Y is x equal mx plus x equal my plus b. Who cares about all this? You just connect the points. That's how a line works. Okay, so that's easy. But how do I connect the points for the parabolic part? So here's where you gotta understand. What does y equal x squared look like? This, yes? What does y equal negative x squared look like? The reflection. What does x equal positive y squared look like? Yeah, from your perspective, shit, let me think. From your perspective, is it, yeah, this, yes. It's gonna point the positive, what does x equal negative y squared look like? There. So isn't it gonna be, right, it's like a normal parabola that fell over, but I only have to draw it from here to there. What's 0 squared?
0.
So it goes through 0, and it looks like a parabola, just opening that way. We draw that in. Are you guys, again, this is what pre-calc should have done for you. You don't need perfect, you just need good enough. Thank God for that, because that is not perfect, but it's good enough. I left mine out in the sun, leave me alone. Now 6-1, it's all about what function's on top, what function on the bottom. This has the same idea, but it's all about which function is closer, which function is further away, because it's going to be R outer, R inner. So if you have them reversed, because you didn't graph carefully, you're screwed. Yes? If you switch R outer and R inner, isn't that going to be a problem? Okay. You're not going to have a good time. All right, let me try to let's see what happens here if I do this. I don't know how you got here, but it's all right. All right. So now I've got this stuff. It's x equals 2. Let's put that in. What does x equal 2 look like? Good. It's going to be right here. Bam, 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 bam. Sugar. All right, you each need to make up your own sound effects.
You will copyright to us.
Okay. And all right, now this is the first one we've. All right. People look at these problems as if each problem is completely different from the one before. Now, how did we draw in our radii before? What did we do? The steps do not change. Where do I start? Where does the radius start? Where is the radius? Any radius, where does it start? At the center. And in this case, what represents the center? Our rotation axis. I love it. Thank you. Right? So it's going to rotate around here. So this is the center. So if I start at the center and I start to draw an arrow, what's the first wall I hit?
0, 0.
No, not point.
Negative
And I pick anything in between here. The first wall I hit, what is that? Good, so the Jeff, dude, start at the axis. There you go, buddy. Good job. R inner, and here's where people get all tripped out. All right. This is x equals 2. This is x equals y squared, right? And negative y squared. How do you always tell how long this is? The bigger one, isn't that bigger? Between this and this, that's bigger for sure, because it's more positive. The bigger thing minus the smaller thing. And what was this wall? Negative y squared. So what's that radius? It's going to be 2 minus y, negative y squared. So 2 plus y squared. You guys see that? So when you draw, you always draw you do your inner radiuses, you start at the axis and you stop at the first wall. Bam! This is negative y squared. This is 2. What's the distance? Well, how do you find the distance between two numbers? Don't you take the bigger number minus the smaller number? Isn't this number bigger than anything on here? So bigger 2 minus smaller, negative y squared, so 2 plus y squared. Right? It's not as amorphous and freaky and vague. It's always that. What else do I draw in now? By the way, real quick, I should have said this. How do I know there's an inner and outer radius?
There's a gap.
There's a gap. Mind the gap. There's a gap between my region and the axis. So there's got to be inner, outer. So now if I can do anything in this region and I go out past that wall. So what is our outer going to be? Well, it's 2, right? 2 minus, and what is this wall? Negative y minus 2. So our outer is going to be 2 plus y plus 2. Our outer is 4 plus y. Okay, I like it. So what are the important steps? If you need to, find where the things intersect. Then you plot the region. plot your axis and you draw in your radii, if the region is not right up against the axis the whole time, you need an inner and an outer. And then I plug in what I've determined into pi integral r outer squared minus r inner squared. And once again, I'm sorry, I should have done this from the very beginning, but I'm silly. This is going to be d what? d1. Why is it dy? Not just because everything's in terms of y, but why is it dy? Going around something parallel to the y-axis. So discs always agree with that. Oh, you're going around the y? Okay, that's dy. That's beautiful, right? What's the limits going to be? Yeah, because it's what y is doing. And what's y doing across this region? You might have just said it. What's y? Yeah, it's going from -1, yes, to 2. And then I put in r outer square minus r inner square.
So real quick,
What if I was at y equals 0? If I'm at y equals 0, this is the inner radius, yes? So I can see from the picture it's 2, right? The inner radius is 2. And sure enough, when I put a 0 into the expression after inner radius, I get 2, don't I? So as I go from -1 to 2, every time I move, the inner radius changes a little bit and the outer radius changes a little bit. How much? That much, right? Does that? So as I move, as I scan, the radii change. Here, the inner radius is 2. What would the outer radius be? Well, what would this point be? If I put a 0 in, I get -2, don't I? So then this would be 4, isn't it? 1, 2, 3, 4. Okay, so you can kind of pick numbers, concrete numbers, and actually see if it makes sense if you want to. You always can. And now it's the easy part, right? This is just the busy work part. This is where you have to FOIL. You get 16 plus 8y squared plus y squared minus 4 plus 4y squared plus y to the 4th. All right, I don't even care anymore. Pi, why did I put a 1 there? So -1 to 2, blah, I don't care anymore. All right. Now, is it really cool that I mean, you just have to do the work. But this isn't interesting. You just get your like terms together. It's just polynomials, who gives a shit? The interval's easy, you plug shit in. Yes, maybe? There's nothing interesting there necessarily. Okay. All right. So a couple of visuals I want to show you, and then we'll call it a day. So you got that business? Put it on you guys. You guys are like, man, this couch stuff just keeps getting better and better. So one visual, is this what I want to show you? No. One visual I want to show you is, here is the teardrop. You can see it right here, right? There's the teardrop thing, and I'm rotating it around the x-axis. And this red thing is a disk. Now remember, the disk, I keep saying area, but it does have a thickness, remember? The thickness is dx. So I've just overstated the dx. It's like thicker than it really would be. Dx is like stupid tiny, but that's, you guys semi with me? So if I add up, so let me see. Here is the shape in full, right? There's the shape in full. So we could take it back to path. And let me turn on my rectangle. Oh wait, there it is. Good. So if I march through, so if I scan from 0 to 2 along the x-axis, every time I move, I'm getting a different disk, and I just add up all the volumes of each of those disks. Of course I'm going to end up with that, right? Especially, and again, right now I got a big ass width. It's sort of like having 4 rectangles when we were doing the area thing, remember? So if I let it go to, I increase the resolution, it's going to be exactly that. That's all we're doing, integrating, adding up all the areas of the disks as I march along. That's all the disk method does. Right? So here's a little preview. Is this a good one? Sure. Maybe? I don't know. All right. Can you guys see? This is not the best one. Did I have mine that I made up? Here's mine that I made up. Okay, sorry. I get so excited for no reason. All right, here's the one I made up. All right. So here's the function, 2y squared plus y, yes? That's the function, 2y squared plus y. And right now I'm rotating around what axis? Can you guys see it? What axis is that? X-axis. So if I wanted to do disks, it would have to be integral dx. Can you solve that for y? Well, kind of could, but it would be so disgusting. Think about it. Can you solve that for y? Try it again. No. Well, you can, but you definitely don't want to. All right, well, I'm trying to get you to understand. Again, I've already sprinkled this in. If I rotate this thing, I'm going to get a volume. There has to be a way to get the volume. There has to be. What I desperately need, disks I can't use. I can't. Because they would need dx, and I can't solve that for y. I can't get it to be a function of x. Yes? But I should still be able to find it. So what we do instead, there's a whole other method that uses shells, cylindrical shells. Oh shit. Right? And all right, so let me show you the visual, and the next time we get to the map of it. So let me turn on my representative rectangle. Notice how, let me see, do they have this the right way? Yeah. Yeah, okay. Notice how my rectangle, in this case, is parallel to the axis I'm revolving around, right? So in this case, we're not using disks. We can't. We just said we can't. We're going to use a new approach. So watch what happens if I rotate that rectangle area, region. Not the region, Jeff. The rectangle. Throw it. So let me look at it this way. What shape have I just created? Cylinder, right? Let me make this a little better. No, screw it, Jeff. You don't have time. So, and watch this. If I move, so what I'm doing right now, isn't this going from, what do I want to say? So as I move what I'm looking at along the x-axis, it's changing. I'm not sure if this is doing this. Okay, I got to play with this thing. I don't think it's doing it the right way. It's not perfect. I got to play with it. Anyway, so what we're going to do is we're going to figure out the area of that shell and then add them up. So it's a different thing than disks. I don't get a nice. Is that like disks are solid throughout? Yes. So they're these flat disks of filled in area that I add up. Shells are hollow in the middle, so they're going to be a little bit different. And again, if you want to get a little preview, I really do like my. I know, but I think this is pretty decent. You can see an example. Little shit and a half. Good. On the other side where it's all colorful, you can see me trying to do shells. Up here. So if I march along this axis and I collect all the shells together, I end up with this. And if I increase the resolution, I end up with the true volume of the whole thing. So next time I'll have a better visual put together. I think I have one, but I can't remember. And we'll get into how that method works. And the main idea of this method is when disks don't work, this method does, and vice versa. So they kind of complement each other. Okay. That's plenty.